So welcome everyone. My name is Murat, Becer. I am head of R&D for Ansys Semiconductor products. So today with me, we have Chip Stratakos. So Chip is running silicon implementation at MedX. He previously worked at Microsoft, in Google, Broadcom, and Intel. And he's a lifelong physical designer, and he's also the self-proclaimed president of the SigmaDVD fan club. And he earned his BS degree from Stanford. So thank you, Chip, for joining us.
Thank you.
And we have Mohit Jain. So Mohit has more than 20 years of experience in VLSI industry. In his current role, he's a principal engineer at Qualcomm, leading power delivery network timing co-analysis efforts. And his background is in standard cell design, macro modeling, SoC power optimization, and low power verification. So thank you, Mohit. So today we have kind of an interesting format. So I'll present only 7 slides in the first maybe 15 minutes to take us through the entire scope of the discussion. And then Chip and Mohit will also talk about 5 to 10 minutes each about their experiences and thoughts about this technology. Then we'll go into a informal discussion, some questions and answers. Then of course you guys are also please feel free. You're welcome to ask any questions. Okay, so let me go into the slides. So we are introducing a next generation technology, a new methodology really going forward in power integrity sign-off. This technology is called SigmaDVD. Now, let me start with updating. Okay, so let me start with RedHawk-SC, right? So RedHawk-SC today is the tool of choice, market-leading product that's enabling semiconductor companies to solve the most complex power delivery networks. As we know, power delivery networks are getting more and more complex. We're seeing 50 billion plus nodes in the power grid, terabytes of collateral, thousands of CPUs are really being required to be able to run these designs in a practical manner. And RedHawk-SC, it's a very modern architecture. It was really a rewrite from scratch about 10 years ago. It has been architected for the cloud, but of course it works as effectively, as efficiently on-prem. It's massively parallel, very efficient utilization, low memory cores. I think it's one of the only EDA products in the market that can support spot instances on the cloud compared to dedicated instances, giving ability to be able to move your workloads to the cloud at lower cost. It thrives on distributed disk. It never needs a big disk so that it avoids network load latency type issues. It's natively distributed, as I mentioned. All the data that's parsed in is always automatically chunked and partitioned. All the algorithms run massively parallel on these pieces of data. No large machine is ever needed. And once the run is done, when you're looking at the results, loading up the database, looking at the GUI, you just need a single CPU, low core memory. And I think most of you, if you are using the tool, you are already aware of these properties of RedHawk-SC. And just to show you a couple of recent examples, these huge designs like 192 billion. It's a TSMC 5 nanometer design. 3.4 billion instances almost, requiring 4,000 cores, and the tool is able to run reliably. And the lower right-hand side, this was a data that was presented by ARM in our IDEAS conference a few months ago. This is RedHawk-SC running on AWS on Graviton 3 CPUs. So this is showing the cost difference between utilizing dedicated instances versus spot instances, right? So the thing with spot instances is that they can go away at any time. So the tool has to be able to support that resilience. The machine goes away, but we are able to continue to run. So, and that gives that advantage for cloud workloads. So if you look at that plot on the right-hand side, that's showing self-drop to full drop ratio. So the summary is a voltage drop on any given instance. Now, the root cause of that voltage drop is not that instance self-switching anymore, but the voltage drop on a given instance is really being caused by its neighbors that we call its neighbors and aggressors. So about 1/3 of the design, in this case, 90% of the drop is coming from these aggressors. Almost all the instances in the design, more than 50% of the drop is coming from these other instances, aggressors. So this is causing a big problem, right? It's causing a big coverage problem. So before, you could run, let's say, RedHawk-SC if you're able to, make sure all your instances at least switch once in, let's say, 10 clock cycles, you would have good coverage, right? But that's only self-switching coverage. Now, every single instance, you may have hundreds of potential aggressors that can switch. So now the search space to be able to find the worst case voltage drop on a given instance is exponentially more, right? So it's very difficult to meet this with transient simulation only. And on top of this, IR-STA is becoming more difficult, right? How do you feed voltages to your timing closure if you don't have high confidence in your voltage drop? And how do you fix these voltage drop problems if you don't know the root causes, right? Which aggressor is causing the voltage drop on this instance? And of course, the designs are continuing to get larger and larger. So just visually, right? If you just look at that one instance in the middle, that's the victim instance. So all these highlighted instances, maybe close to 1,000 instances, are potential aggressors that when they switch, they will cause a voltage drop on the VDD or VSS pin of this instance. So think about this. You have millions of potential possibilities, scenarios for a single instance. And in your design, you have, in a block, you have 10 million instances, right? In design, you have 100 million, billion instances. So search space is huge. And at the end of the day, what you really need is analysis that can run billions of cycles, billions of scenarios to be able to get a high confidence voltage drop on every instance of the design, which is not possible, right, with just transient. So so this is exactly what SigmaDVD at the core is solving, right? And I think it's a good analogy. What I'm showing up here is, think about the days of dynamic timing simulation and how it moved to STA, right? So this is this kind of a technology and a transition going from transient towards SigmaDVD. And if you only stay with transient simulation, right, there are many limitations. So as I mentioned, aggressor coverage is one of the biggest ones. There's not enough cycles of simulation, transient simulation, to be able to get high coverage, high confidence voltage drop numbers. And also in transient, as we go to more advanced nodes, currents are sharper, we are reducing time step, right? So that's also increasing runtime. Results in transient are always sensitive to small changes. So the conclusion is really so I'm not saying transient is going away. Transient is important. We still need transient especially for example, chip to package impacts, low frequency noise at the upper metal layers, dynamic electromigration, or you have some specific vectors, VCD, FSTB, that you want to run and test, enabling hierarchical methodology. So these are all good. We still need transient, but transient needs to be augmented, or it needs to be enhanced with this high coverage technique that we call SigmaDVD. And we will go into these applications in the next few slides and when we also discuss. So SigmaDVD is the technology that is addressing the challenges that I just talked about. So it is invented and patented by Ansys. It has AI algorithms running under the hood, but these are not AI algorithms that you have to train externally. These are really AI smart algorithms that are running under the hood. And for a given instance in your design, every single instance, we look at all the potential, let's say 1,000 potential aggressors, timing correlations, logic correlations, various risk factors, and we figure out the worst case practical voltage drop on that single instance. And we do this for all the instances in the design. So it's computationally. So think of it as if you're running millions of transient simulations to find that practical worst case noise on every single instance. But it's computationally very heavy, but because of the patented technology and also the Seascape parallelism, It's actually very, very efficient. So we will hear the experiences from Mohit and Chip. It's very fast. It gives you this almost 100% coverage on high frequency simultaneous switching noise. It gives you analytics, meaning if I have this voltage drop, what is the reason? How much of it is coming from self-drop? How much of it is coming from aggressor 1, aggressor 2? And it's very fast, as I mentioned. So now because of these capabilities, so this is the core technology, SigmaDVD. With using SigmaDVD, we've created applications that can easily fit into the design cycle. So here today, we're going to talk about 2 of these applications. So one is SigmaPD. So this is the SigmaDVD application for dynamic voltage drop avoidance or prevention early in the design cycle during place and route. When you're doing your placement iterations, when you have a version, you run SigmaPD. We use the insights, it's very high coverage insights, to generate directives that can go into a commercial place and route tool and improves the design and does this avoidance very early in the design cycle so that sign-off is much more faster and more easier going forward. And SigmaAV, and this is a quote from one customer, SigmaAV is a killer app. So this is the SigmaDVD application for high coverage sign-off. So if you look at this chart, transient, right? When we only run transient, we have a single voltage drop number, and we don't know the root cause information, right? But what we did is we combined the best of transient with SigmaDVD. That resulted in this technology called SigmaAV. Now with that, you not only have this very high coverage in your design in terms of voltage drop point of view, but you also have very precise root cause information. How much of the drop is coming from the package, how much of the drop is coming from this low frequency regional drop, from self-drop, from individual aggressors. So what that enables, of course, is now you have this very valuable information to be able to do very effective, very efficient ECOs. So you fix the things that need to be fixed. And also what that enables is that you have this very high confidence, high coverage voltage drop number on every instance. So you can now confidently feed it to a timing flow, right, to your STA tool. Again, we will discuss these more in the discussion today. So in summary, this is my last slide. So SigmaDVD going forward, it is enabling an overall methodology upgrade. It's delivering this comprehensive DVD coverage for all high frequency simultaneous switching, neighbor switching scenarios. The application of SigmaDVD called SigmaPD is enabling early dynamic voltage drop prevention during place and route. The other application, SigmaAV, is enabling very high coverage sign-off, which is also providing all the root cause information, which is of course enabling very efficient ECOs, and it's also enabling a very high confidence voltage timing flow. So it's, at the end of the day, it's dramatically improving design workflow and TAT for better PPA for semiconductor design. So, okay, let me leave that up there. And so that's the overall introduction to the technology, the applications of the technology. And now I will leave it to Mohit and Chip, so they will share some of their experiences and thoughts with this technology in the recent year or so.
Should I go first?
Yeah, please, Mike.
Thanks, Murat, for a very great introduction to the SigmaDVD technology. I think it's going to help us a lot in connecting some of the questions which you guys will have, and I think which Murat will ask, to the answers that we will give. So in terms of experience, first of all, as we all know that the DVD or the airdrop has been really a serious challenge for over many generations of chips. And it's becoming increasingly prominent as more and more devices are getting packed into smaller areas, and they have to support heavy AI workloads and high performance compute applications. Now in Qualcomm, we really focus a lot and put a lot of efforts in ensuring that any potential risks to our devices' performances, if it's getting affected, can be exposed during pre-silicon stage through some exhaustive analysis. And to an extent, we have been successfully able to deal with this risk, specifically for some target applications like test modes, where the activity is still fairly well directed. Like the scenarios are quite fairly limited. But for the functional scenarios, it still remains a huge challenge just because of the sheer complexity in the sheer number of scenarios that can be generated. And this is what I think Murat has already mentioned. So unfortunately, for functional mode, we still have to rely a lot on the vectors for any IR drop sign-off. Now, we have, as we said, that the number of applications, the number of scenarios, modes, functionalities have been increasing with every chip. So even securing these vectors in pre-silicon is almost impossible. We really cannot rely and depend upon all these vectors availability to make sure that our chips do not see any unexpected variations on post-silicon side. So we really have been looking for a comprehensive, controlled, and compute-efficient, very much vectorless-like technology and approach, which can give us a very high confidence, very high design coverage, without incurring a lot of millions of cycles, and at the same time, make sure that it maintains very well global as well as local power targets. And I think SigmaDVD fits into that solution space very well. As Murat mentioned, that SigmaDVD provides a statistical bound for the localized switching noise by creating thousands of scenarios around each instance, and it does that quite very fast. And we have some numbers which shows that it's relatively much faster than the transient analysis. So I think SigmaDVD is a very promising solution, and really we have not just evaluated SigmaDVD as a technology, but also the derivative applications which Murat highlighted, which include SigmaPD and SigmaAV, and also the IR ECO capabilities. And it really provides an end-to-end solution, starting from giving some directives or giving some guidance to the physical implementation tools, down to providing a robust way of analyzing the IR drop, and then taking it all the way to the ECO stage. So I think overall it's a very promising tool suite from Ansys, which is going to help us a lot going forward. The main challenge that remains, and that is my last comment, is really how do we handle the results that come out of SigmaDVD? Because in the current form, sometimes depending upon the nature and characteristic of the design, the number of violations can hugely grow, and we really have to spend efforts in segregating those violations into must fix versus good to have fix versus waivers kind of things. And on top of it, we also have to come up with a smart way of fixing these violations. What is the best fix strategy for these violations? And that's where I think voltage timing, flow, co-analysis is really important. So we really want to focus more on how these voltages, the drop distribution impacts the chip's performance, and then take those back into ECOs. So that's what my experience has been.
Yeah, thank you, Mohit. Thank you. Chip?
My mic on? Okay. I'll start out by pointing out that my name is Chip, and I'm a chip designer. And if you thought a few minutes ago that you were onto something, it's not original. That one's been overplayed. Okay. Let me also acknowledge two of my colleagues who are here, Mehta and Pranav. They did much of the work that when we worked together on a chip at Microsoft. So I'm going to lean in a little bit stronger than Mohit. The vice president, it's an important job, but as the president of the fan club, I'll lean in a little bit harder than Mohit did. How many people here are signing off a really big complex chip for timing using SPICE? Anyone using SPICE exclusively? Didn't think so. I think the same thing about transient. I can't imagine signing off a big complex chip using transient. We tried it. It was very painful for a number of reasons, but I think that's old news. And I'm all in on the SigmaDVD technology and using SigmaAV as the sign-off at the block level. As Murat mentioned, SigmaPD is also a very powerful capability. We saw a lot of good results with that. Transient still has a place, but mostly for above the block. Complements, SigmaDVD with SigmaAV, and then used for above the block and modeling the chip, et cetera. As Murat mentioned, the biggest challenge with transient is the coverage. It's enough of a struggle to get every instance to switch both up and down during the finite analysis window, but the if we go back to the picture of the, coupled aggressors and realizing that the aggressors is the majority of the drop. There's just no practical way to select the right aggressors. And furthermore, it's not just selecting them, but aligning the timing of them. If there's this timing window, you have to believe that the switching can happen at the wrong time. And with transient, it's a roll of the dice, exactly the selection and then the alignment of the aggressors that are selected. So for me, it's not even really a question. Yes, you can see more violations using SigmaAV than you would with transient. I think that's proving the value as opposed to being the problem of it. One of the most exciting things that I see with SigmaAV, and which I'm leaning in hard also, is the IRSTA. And specifically, once you believe that you're getting the full coverage in SigmaAV and you're actually seeing the realistic worst drop on a per instance basis, now you could have the confidence to back annotate those drops into STA for setup analysis and eliminate this margining that happens on the interface between STA and IR. And when you do that, a couple of really great things happen. The first thing is the slacks improve, because instead of assuming, let's say, a 10% drop on every single instance, right? What you find out is the median is probably closer to 5%, okay? There may be some 10s, but there's gonna be some 5s and some lowers, and what you'll see is the slacks improve pretty much across the board, okay? So the first thing you can say is that makes closing timing easier, and it's true. It also means that if you can absorb the IR drop, you don't necessarily need to fix to 10%. You can tolerate larger drops. And then with the better slacks, you can then do more area and power recovery if that's important to your product. And then lastly, when you do have an IR drop violation on a timing critical path, you now have a choice to think of it as a setup violation or as an IR drop violation. And given the very mature timing ECO capabilities that we have in the industry, I would argue that solving those as timing violations is a heck of a lot easier and more productive than trying to fix them as IR drop violations. So all of that IR STA thing would be extremely risky to do based on transient because of the coverage issue. So it's really that solving the coverage problem that opens up the door to removing all of this margining between STA and IR. And to me, that's where a lot of value comes in. And I expect that as more and more people appreciate that will become kind of standard practice going forward.
Yeah, thank you, Chip. Yeah, thank you for all the comments. So in the rest of the discussion, we will, double click on some of these items that were highlighted by the three of us, and maybe dive a little deeper, show some data also. So if we step back and I guess rewind, and review everything we discussed. So we talked about challenges first. So I think this part is pretty clear, right? The number of aggressors is very high. The ability to be able to switch everything, right? Coverage in transient, that's very difficult. Anything to add more on the challenge side of things with transient?
I think the runtime is automatically basically part of it. If you want to really get a higher coverage, you either have to run the simulations too long, or you have to make the scenarios too pessimistic by increasing the power targets, and both of them have either an impact on compute, tape out cycles, or your eventually it's all the tape out cycle will get hit.
Right. So overall TAT.
Yes.
I think even running it longer. I don't know how you know when you have enough coverage.
That's true.
Right. I mean, coverage will go up, but
confidence.
Yeah, it's really hard to know. It's kind of elusive. So that's one problem. Another thing that so that's kind of the optimism that transient has because of the coverage holes. There's also a pessimism that exists with transient, maybe not as obvious, not as impactful either, but I still think important, which is transient will report the worst drop that the instance ever saw during the entire simulation, okay? If that drop happened when not when a timing critical path is going through the instance, it's not clear that you need to fix that. It doesn't impact setup, right? So in addition to we're not catching all of the problems, some of the violations that we're fixing need not be fixed. That's a problem.
So wasting power, performance area.
Yeah.
Okay, so
time,
then
schedule.
and schedule, yeah. So then in terms of putting SigmaDVD technology, right, how does it fit in the design cycle? We talked about SigmaPD, SigmaAV. So if you start, if you go back to SigmaPD, right, so this is, of course, early in the design cycle, right, shift left, if we can prevent dynamic voltage drop problems in this very high coverage, high visibility manner, right, that has huge value. Any additional thoughts?
That's right. So I think, as I mentioned, that SigmaDVD technology really enables multiple applications, and it spans all the way from placement all the way down to the ECOs. So SigmaPD, which again uses the identification of aggressors, and it can clearly demarcate which instances have a higher contribution of self-drop versus the aggressor's drop. So once it collects that information, then we can direct the placement tools to, so for example, if there are 10,000 violations, out of that 1,000 violations are because of high self-drop, that means either there is a problem with the weak grid, or the cells are very high current consuming and there is no way those can be controlled within the threshold limits. So there can be different ways of fixing that. So if it's a grid problem, of course, go ahead and beef up the grid or do some local PG fixes around it. But if it's a high current driver problem, then we really have to use those cells in a very scrutinized way and not really spread them all the way around. And similarly, if it's more of an aggressor's problem, then we can give some directives to the placement tools to really group some category of cells and make sure that those are not placed very in close vicinity, or maybe we can add some skew in those kind of collection of cells. So different techniques can be adopted, but SigmaPD provides a platform for the physical implementation tools to really provide you a correct by construction design. So that's where SigmaPD fits in. SigmaDVD, which I think an extension of it is SigmaAV, which is a hybrid approach of transient analysis plus.
We'll get to SigmaAV.
We'll get to SigmaAV.
Yeah, so for now, let's stick with SigmaAV.
Right, and I think the last part is the ECU capabilities. So that's also where the diagnostics capability of Red Hawk SC can be leveraged into generating the ECOs, which can be much more effective than, as Chip mentioned, that rather than fixing all the violations which are not even affecting your timing, we need to bring in the timing aspects of the chip and the blocks, and then make sure that whatever fixes we are building in, they are very effective without having least disruption into timing and physical implementation.
Yeah, thank you, Mohit.
Going back to the IR ECO capabilities are very weak compared to timing ECO capabilities. A natural conclusion from that observation is we better prevent as many IR violations as possible, right? Because the ones we have are super painful to fix. We're just not that good at it, right? So we did two things. SigmaPD, I'll say second. First thing we did is we used SigmaDVD extensively in the design of our power grid for a new node, right? We had one design that was particularly demanding, and we used SigmaDVD extensively to inform the power grid design and push it to the edge of, close to the edge of routability so that we would have as robust of a grid as we could afford, right? That goes a long way to reducing the number of violations. Secondly, we used SigmaPD in a co-development phase rather extensively, and the results were astonishing. To say again how it works, it looks at placement N-1.
I will actually bring up that one slide.
Sure.
This was presented by Microsoft in our IDS conference a few months ago, and this is, I think, along the lines of what you're talking about, Chip.
Yeah. So using the results of placement database N-1 and looking at the violations and applying some rules that can be then fed into placement version N to avoid some of the interactions that were observed in N-1. We saw astonishing reduction in the number of violations and really at no cost to QOR. It was quite surprising. Hundreds or even a few thousand directives or cell movements, and it pretty much cleaned up the IR problem and didn't show any appreciable impact to any of the other QOR metrics. And much more good results than I expected. The big takeaway for me is the designs are a lot more flexible than we think they are. We think every little thing has to be exactly perfect. And the result of this, when you see the quantity of movement and degree of movement between the two databases, there's a lot of flexibility in the design that we don't appreciate. And this technology exploited that and really did a great job in reducing the number of incoming violations.
Yeah, thank you, Chip. So as Chip explained, and as you can see in the slide, and this was presented publicly in our IDEAS conference, so this design started with that blue histogram, where if you have 10% voltage drop as your threshold, you have hundreds of violations. And through SigmaPD, these directives were generated that were fed into the commercial place and route tool. And after 2 iterations, the histogram moved to the green histogram. So at 10% drop, all violations were eliminated or prevented, avoided. And if you look at it, the entire histogram shifts left. So what that means is you reduce your Vmin, right? And when you reduce your Vmin by 3%, now that gives you flexibility, as Chip and Mohit were saying. You can use it to maybe reduce some area or some recovering some power or improve Fmax. And this is the type of results we're seeing at several customers. Thank you. Okay, so let's move then towards the other application, towards the sign-off area. So here we talked about SigmaAV. So this is combining transient effects that are needed, right, to get a complete picture, such as the low frequency noise at the higher metal layers or mid frequency noise at the kind of the middle to upper metal layers, but combining it with the missing coverage of just pure transient with the coverage information, with the high coverage simultaneous noise that's happening at the lower metal layers at the instances that are switching at clock frequency. Right? So the combination of these is SigmaAV, and that is giving us this very high coverage, transient looking simulation, and very high coverage voltage, very high confidence voltage drop numbers on every single instance. So what do you think? What are thoughts in this technology, the benefits?
Exactly. So when we really first started evaluating SigmaDVD as a technology, we were definitely amazed, and we really thought the technology is really powerful. But when it came to the point whether you can replace your current transient-based analysis approaches with this SigmaDVD for sign-off, that's where I think there were some concerns, because as a whole SigmaDVD, the way it is brought up, it is not really meant to capture the high layer drops plus the package drops, because it's not doing any transient simulations. So that's where we were concerned, and we raised this concern to Ansys that if we really want, and we really do not want to do multiple of analysis, like you do SigmaDVD, you do transient vectorless, you do transient VCD, we really don't have that much compute, and we really do not want to spend that much time on analysis to make sure that our chips get signed off. So what we want is, we have our current traditional way of signing off my IR drop through transient way. How can I replace it with Sigma star DVD? And that's where I think SigmaAV came in, and Ansys did a good job in giving us this technology very quickly, and not waiting and spending another year down the line to fix the problems that we raised. So what SigmaAV really does is that it finds the missing component of the global drop. So really what it's all doing is it's helping us to visualize the voltage variations in the same breath as we use for process variations. Even for process variations, we have two components. There is a global process variation, there is a localized process variation, right? And we need to make sure that both of them are handled in the same breath. And that's what was missing from SigmaDVD. While it was fixing the localized variations of voltage noise, it was missing the global noise. And for that, SigmaAV, what it does is it uses your transient analysis as a baseline, which still doesn't have to run for thousands of cycles. It just has to maybe run for 20 cycles to get a fair estimation of what your global drop can be. And once you have that information, you can really superimpose that information with what SigmaDVD gives you. So here, you are getting a comprehensive coverage by creating all thousands of scenarios around each instance. And at the same time, you're not missing on the package drop and the high layer drops, which are caused by rest of the design activity. So now SigmaAV has a potential to really replace our traditional methods in terms of sign-off. And I think there are still some intricate analysis which needs to be fine-tuned, and we need to make sure we need to make something on top of SigmaAV. But as a whole, SigmaAV is a very promising technology to be useful as a sign-off technology for IR drop.
Yeah, thank you, Mohit.
Yeah, SigmaDVD came first, and if the story ended there, it would have been very useful in kind of in the construction phase, in guiding the design to a more robust state. But the addition of the SigmaAV layer on top of that is what makes this, in my opinion, sign-off quality tool. And I'm super glad that that's the direction that was taken, because just SigmaDVD and then signing off with transient wouldn't really solve the problem to the extent that it's solved now. It's really that marriage of the transient with SigmaDVD together, called SigmaAV, that makes this a sign-off caliber kind of tool. And then you get the benefits through the whole flow, and all the way through to the IRSD. All of the goodness comes together once SigmaAV can be thought of as the sign-off tool.
So do you think SigmaAV will eventually replace all vectorless transient today?
For me, it already has. Even vector-based, I see no real practical need for it. There are, modes that need to be considered. Maybe if you had a very complex situation, maybe there could be a case. I still don't think so. But in a simpler design where the use cases are finite, I don't even see a good use case for a vector-based approach. So to me, it is the one and only sign-off that's needed.
Thank you, Chip. Mohit, what do you think?
Well, you may hate me for saying this, but it's not there yet. But that's our goal. We want to really replace SigmaAV with the traditional ways of signing off IR drop with transient methods. But SigmaAV is a transient way plus some SigmaDVD. So what we really want, our goal is to safeguard our designs from voltage variations, not just from the known vectors, but also from the unknown vectors. And that's where the big challenge is. Like, we have to fabricate the vectors using SigmaDVD and SigmaAV in such a way that it holistically makes sure that my designs do not see any yield loss or any V-min excursions once my design is now put on silicon. So that's a big ask. It's not even there today, but that's how we are trying to utilize or leverage this whole platform. And by doing that, it will be in a transition mode. So maybe for a few years, we might use a mix of transient analysis, some vector-based designs, plus the capabilities of SigmaAV. But once we have full confidence in SigmaAV, when we know that it uncovers all possible scenarios different vectors have thrown out, then probably we will move to the SigmaAV-based approach completely.
Okay, so you're saying it's going in that direction?
It's going in that direction.
So how about, when Mohit was initially talking, he talked about the additional pessimism, right? The additional violations that come up. So what do you think about that, Chip?
You mean the late edge thing?
Yeah, the additional violations because of
Oh,
the
yeah, yeah.
coverage. Right?
Okay.
So how do you deal with those?
Yeah. So when you first look at Sigma AV compared to transient, it probably will be the case that you see a big increase in the violation count. And again, I think that speaks more to what's being missed by transient than pessimism in Sigma AV. At least that's my belief, and I think backed by a lot of good engineering on both sides. So the way I think about it is if that's more than what you can afford to fix, one of the nice things about Sigma AV is that it has this risk knob. In traditional statistical methods, you can dial it in. Let's say I think of it more as I have a fixed amount of engineering bandwidth I can spend fixing IR drop. You can dial in the risk factor to modulate the amount of violations. To me, there's no clear pass-fail line. It's all, how much you want to put into the product, how much risk you want to take on silicon. And by the way, risk is, in a lot of cases, it's just how many millivolts you need to boost the power supply by to still meet timing. So risk it's not like chip is going to die, right? So to me, I think of it as, we can modulate the amount of effort we spend fixing the violations by dialing this risk knob. Also, when you get to the IR-STA stage, the violation count goes down dramatically.
Yeah, thank you, Chip. And also, if we with the full capabilities of SigmaDVD deployed, if you're using Sigma PD early in the design cycle,
that's right.
Right, then you are already addressing and avoiding most of the problems. And actually, at that point, when you run Sigma AV to that kind of a design, you actually end up with a very manageable but very high confidence, violation count.
I also think there's an important role for BQM in the prevention side, which is a little bit orthogonal with the SigmaDVD, but another thing that helps, again, the ECO capabilities suck, so let's make sure we do everything we can to limit the number of violations that pop up, and BQM is an important technology there that helps with that.
So yeah, let me actually show one slide on Sigma AV. So this data was presented by Microsoft in our IDEAS conference a few months ago. So again, to summarize what Sigma AV is it's SigmaDVD enhanced transient analysis, right? It's combining the best of SigmaDVD with a transient dynamic simulation. It's accounting for local simultaneous switching noise with very high coverage through SigmaDVD, but it's also accounting for the background noise, right? The package drop, top metal layer, low frequency noise. So here, this plot, x-axis is the voltage drop from just pure SigmaDVD. This is based on local noise. And y-axis is the Sigma AV noise. This is the comprehensive, including everything. And if you look at it, that blue region, 98% of the instances in this block are in that blue region. And that's about 4% of VDD, voltage drop. But then if you look at outliers, right, there are instances out there that are more than 10% of VDD. So, and you're getting this, to get to this picture, with transient only, you would have to run, I don't know, a few billion cycles of simulation, basically, right? So this is a very high confidence voltage drop visualization, right? What can happen? And so through this, this is a very good, I think, segue into voltage drop on timing, because most design flows today, again, we're going to hear from Chip and Mohit, we're feeding some kind of IRD rate, right? Maybe 10% of VDD when you're signing off timing. Why? Because we don't have the confidence on the coverage of voltage drop. But now with this picture, because you have this very high confidence, most instances have 4% voltage drop, and you're very confident about that. So instead of feeding 10%, by feeding 4% voltage drop to timing, that's margin recovery, right? With that, you can do power savings, you can do area savings, you can do timing improvement. But then you're also catching some real timing silicon escapes, potentially, right? Because there are high voltage drop instances And if they are on timing critical paths, if they are affecting your frequency, those are the ones that you really need to address. So it's giving you that insight. Any other comments on this one, Mohit?
I think absolutely. So I think long gone are the days when we would just sign off based on voltage drops, because there is no way we can manage within 10% limits. You will have, I think, depending upon design to design, you will have tons of violators which you cannot fix, and there is no real benefit of fixing them. So we have adopted in Qualcomm this voltage timing flow for many years now, and it is becoming more and more advanced and accurate, to the sense that even when we give this voltage feedback to timing, we've carefully engineer on what voltage we are feeding it. It's not maybe the default voltages which come out from the Red Hawk tools, because those are meant for IR drop sign-off perspective, but how much do they align to the timing criticality of my timing paths? That's altogether a different ball game. So we really pay a lot of attention into how voltage plays a role into timing. So that means if there is a drop, how can that impact timing, versus if there is a timing criticality, how does that impact the voltage drop? So both this co-analysis of PDN into timing and timing into PDN is very important. And yeah, I think that's the way forward. We really have to bring in the timing aspect when we have to fix the amount of violations that we see as a result of this analysis.
Thank you.
Yeah, leaning in on the IRSTA, I'll take the voltages right here from this chart and annotate it back to STA, and I'll still argue that it's conservative, because when you do that, you're assuming every instance will have the worst drop that it has ever seen along that timing path. And the chance of all of those things lining up is small. When it does, I'm covered. And when it doesn't, then I have even a little more headroom. So even if there's some question about whether it's precise to the millivolt level, I believe there's still a fair amount of pessimism in the assumption that every instance will see its worst drop simultaneously. So for me, I'm good with these voltages straight into STA.
Yeah, I agree. So even though there's built-in pessimism, but still the voltages, as you can see, are
it's a
very
massive,
practical.
massive
and still
relaxation.
much better than the IR. So, and that, if you look at this slide, this is actually being presented by Microsoft in this conference, I think, tomorrow. So using this methodology, so on the left-hand side, if you look at the timing slack histograms, the red histogram is using margin-based voltage feedback into timing, and the blue one is using the SigmaAV voltages, as Chip was mentioning, directly into timing. So you can see the improvement in slack. So this is improving Fmax, and you can see the positive slack paths, which are opportunities to improve power and area. And on the right-hand side, it's basically the same information or the same design, or two designs. The 4 bars on the left-hand side with the margin base versus the 4 bars on the right-hand side with the SigmaAV-based feedback. You can see the reduction in WNS and TNS and number of violating paths and the power recovery that has been accomplished because of that additional margin recovery. So I think this speaks to what you guys mentioned. Okay, great. So how about overall? So we talked about the technology. We talked about the key applications, SigmaPD, SigmaAV. We looked at benefits. We looked at some data. So how about your experience and thoughts on what the ease of running these applications, or ease of adopting, bringing in these applications into the design flow?
I think it's quite. I mean, particularly, I didn't face any challenges. I mean, our teams have been exploiting it for quite a while now. It just requires you to generate some additional views like aggressors view, the voltage impact view, which again are as straightforward as doing extraction or timing view generation. As I mentioned, when it comes to incorporating into the design flow, it's not really implementing or generating these SigmaDVD analysis and its output, but what you really do with these output results. Because as I said, in some cases it can become so challenging to consume these violations that we have to carefully examine what out of these violations are coming just because of the self-drop. So that means those are must fix anyways. How many of those violations are coming because we have overly exercised the aggressor rate around certain set of instances. So that's where more deeper analysis into. We also have to, in those cases, we have to also go with the architectural information. Can those aggressors be simultaneously active? So we have to really go back and forth with the RTL teams and design teams, understanding how much of that is really practical, and we have to tune back to come to the right balance that where the amount of violations are really consumable. So I would say in terms of the flow itself, it's kind of seamlessly and easily integrable. But what we do with the results is a more challenging part, which is on the design team side on how to really leverage it, not on Ansys side, I would say.
Yeah, thank you, Mike. Chip?
Yeah, similarly, not so many technical challenges. I mean, we were an early adopter, so there's a learning curve. But with the flow that got deployed, not so many technical challenges. There is a little bit of inertia of getting everyone aligned that this is safe, and it's a paradigm shift, and that takes some time. But we were determined and plowed forward. But takes some time to get everybody on board. So I think the challenges are more in that space. Obviously, the productivity of fixing the violations which don't go away through all of the techniques we mentioned is still a bit of a challenge. And I look forward to seeing better and better ECO capabilities that will help address that problem. I've heard anecdotally they're out there. I just haven't experienced them myself. But I think to me that's the next frontier, is to have high productivity fixing algorithms.
Great, thank you. So how about the impact on hardware cost? Right. So as we know, DVD analysis is really one of the heaviest compute consumers today in terms of the EDA flow. Right. You're needing many machines, many hours. Right. That's cost, whether you're running on the cloud or on-prem. How do you think this technology, this shift, is going to affect that side?
Definitely, it's going to translate into optimizing and reducing the hardware cost quite significantly. But I won't put any number yet on that because, as I said, it's still some way, there's still a way to go before we really replace all our current methods of transient analysis into SigmaDVD. So once we really go to that production scale, that's where probably we can give a more definitive number of how much has it translated. But definitely, we had a very good comparison of different tools, starting from front end down all the way to the physical implementation of how much tools fare in terms of distribution of their LSF, the sharing farm distribution. And RHSE stood out in that. So that shows that, yeah, our current traditional methods are really very costly on compute, and there is a big push from management side that we need to cut down on that. And the way our design sizes are getting bigger, we are expanding into auto space and other larger chip design applications. So in that regards, I think it's very imperative that we need to move into these compute cost saving technologies. And I'm sure SigmaDVD will do that quite greatly.
Yeah, thank you, Mike.
I think on our experience, we might have had a simpler baseline flow, transient flow that we started from. And when you think about Sigma AV, what you're kind of doing is leaving that transient flow there and adding to it the Sigma DVD analysis. So on our side, it does increase a little bit the demands. When we run in our flow, we run the Sigma DVD and the transient in parallel, and then there's a step at the end that merges and collates the information. What we find is the Sigma DVD, maybe it's a function of the hardware that we use, but the Sigma DVD runs quite a bit faster than transient. So we're running Sigma DVD in about half to 2/3 of the time that it takes us to run transient. So from that standpoint, we don't add any runtime, but we do add the extra compute of running the Sigma DVD in parallel, and plus the merging step.
Yeah, great. Yeah, thank you. And if we try to improve address the coverage issue through only transient by adding more and more cycles,
then the
right,
comparison
compared to that, of course, there's a huge savings.
Yes.
Yeah.
I mean, for the same coverage, of course, what we would end up in spending on compute would be much higher with the traditional methods, and that's where I think it brings a lot of great value.
Exactly.
Yep.
Okay, great. So that's the questions I had. Did I miss anything? Any other topics you guys want to bring up? Or
I think
questions?
I would like to say a bit more on the ECO capabilities, since Chip has been highlighting about automated and highly productive ECO capabilities. So just to let you know that we are also exploring this solution, which is jointly co-developed by Synopsys and Ansys, which is tweaker based currently. So that uses this native diagnostics capability where all this aggressor contribution and self-talk contribution database is available. So these timing to ECO tools like Tweaker are very well able to leverage this database. And since Tweaker already has the timing background to it, so it knows that which aggressors are more effective in doing any what ifs and swaps, and which have less impact on timing. So Tweaker, along with Ansys, has developed this capability where you can, simply give all this database to Tweaker, and it can generate automated on-the-fly IR ECOs, which are timing aware. So we have been pushing for it, and we have been really experimenting this with a lot, and it is showing promises to us for at least the designs which are not highly timing critical. Of course, the blocks where there is a lot of timing criticality, there you will have challenges in making sure that you don't, disrupt the closed timing designs. But in general, I think it's a great value.
Yeah, thank you, Mohit. Yeah, so this is the IR ECO flow that Mohit is talking about, and without this information, right, with SigmaDVD and IR diagnostic, we are able to provide the root cause information to Tweaker or Prime Closure, so that the ECO tool knows, okay, these are the violations, but these are the reasons of the violations. So let's say you may have 1,000 IR drop violations, but maybe there's only 100 aggressors that are responsible for most of that voltage drop. So now you only do 100 ECOs instead of 1,000 ECOs, and that's the additional efficiency.
Exactly. Yeah. So the amount of ECOs are limited. So and at the same time, the good thing is it's really helping your power, because mostly it would downsize your aggressors. So it comes at no cost. If those aggressors are not timing critical, you are even saving the leakage for your design. So it's a win-win situation.
Chip, anything else on your mind?
No, I think if there was just some way to get Ansys and Synopsys, a little bit closer together.
Maybe that might be happening.
Yeah, that would help a lot, I think.
You already see that happening.
One can hope.
Okay, great. How about questions from the audience? Yeah, please go ahead. Thank you, Ted.
Can you hear me?
Yes.
Okay. Yeah, so there's a couple of questions. So with this approach, you're not running transient analysis. Does this change how many modes or which PVTs you use to run your screening for IR drop? For example, maybe in the past you might have just evaluated one or two corners, and you might have just looked at functional, but maybe now you're looking at test and multiple corners, etc.
Yeah, if I understood correctly, like with IR-STA, you may need to do IR at more scenarios to match your STA scenarios. Is that?
And corner also, yeah.
Yeah. Scenarios, I meant corners, yeah. Okay. Yes, if I were signing off with many corners for setup, then I would probably feel compelled to do the same for IR. In the case of the product I was working on, that wasn't a problem. We had a very simple setup sign-off, so it kind of came for free that the IR analysis and the STA analysis corners lined up very nicely. But if I was signing off, 24 or more STA setup corners, perhaps I would feel more motivation to expand the IR corners. It's kind of expensive, so I might look for another solution that was that left a little bit on the table, but didn't bring any risk, right? So you have to decide what's most important to you. But perhaps, yeah, more corners in IR might be needed to couple that with the IR STA.
Yeah, I mean,
And
in my mind,
sorry, one more thing. I didn't say this explicitly, but with the IR STA that I'm such a big fan of, it's not for hold. Okay, so I don't recommend changing hold in any way. I don't want to reduce the hold fixing by looking at the IR drop or anything like that. So in my mind, hold was like untouched, and it's just a means to apply this in setup analysis. Okay, and even that may be for let's say binnable domains, right? In a fixed voltage, fixed frequency domain, it's kind of more like a hold situation where you're going for that 100% yield. Maybe there I'm also not as adamant about the IR STA, but when I have a binnable setup domain, that's where I think the most value comes.
yeah, agreed. And as you were saying, I mean, ideally, for every STA corner that you're signing off, you need the relevant voltages for that STA corner, right? And this, I think, because of the efficiency of the compute, this is enabling in that direction. But as Chip said, of course, there are more engineering level solutions. But I think this will enable to be able to run power at more corners so that you can feed the relevant voltages to STA.
Yeah, I think if your question is that does this technology enable you to do more IR corners than what we usually do, I think yes. And I do also feel the need that we should have probably more number of IR analysis corners than what we do traditionally. We should have one specific IR analysis for test modes. Even in test modes, we have multiple. We have ATPG shift modes, capture modes, and then we have MBIS modes. So there are whole plethora of test modes. So probably we need to pay more attention of what modes captures what. So probably covering one test mode should be good enough, and one MBIS mode should be good enough, and functional modes are one. When it comes to going for the PVT case, I think that's where we can be a bit conservative, like signing off for the most conservative PVT corner, which could be the highest performance mode corner, and be assured that that should cover most of your lower mode corners. The transition comes when you go for a very low voltage mode. So when I say very low voltage mode, where the inversion happens. So that's where the impact of voltage on timing changes drastically. It doesn't go linearly as you go from, let's say, 0.8 volt, 0.7 volt, where you are in the linear range, versus to below 0.5 volt. That's where I would still recommend to do one more set of IR drop analysis to be more accurate on how your voltage variation distribution looks like. Otherwise, the drops can be overestimated coming from the higher corners, and you may end up paying high penalty to fix those setup violations for the lower voltage corners. But yeah, if your question is whether this technology enables you doing that, I think so. It should.
Thank you. Any other questions? We have time for another question.
Hi, do you have a similar solution for transistor level custom?
Can't hear. Can you hear?
Yeah, it's not very audible.
Okay. Can you hear me now? For transistor level, like totem.
Totem.
Yeah, so the question is there a similar solution for transistor level power grid analysis, like for analog mixed signal level designs for totem SC solution? So it's nothing in production yet, but it is on the roadmap. So in the next few releases, yes, we are working on that. Thank you. Okay. And, So I also wanted to make sure you guys are aware of so there are 4 SigmaDVD papers being presented at this design automation conference by SoC, ST, NVIDIA, and Microsoft. So these are listed here on the slide. And if no additional questions, I would like to thank Chip and Mohit. Thank you for being here and sharing your experiences and thoughts. And we think this is really a game-changing technology going forward, helping us improve overall design cycle, TAT and PPA in all semiconductor designs. So thank you all.